This is a video on really the definition of integration and the connection between integration and the limit process, which we've talked about a little bit in class, but this is kind of a more formal explanation of it. And this is also talking about evaluating limits as n approaches infinity, which is a skill that you need to have to be able to understand this process. So first of all, let's look at the definition. And then it's written out here. It says the definition of the definite integral, and that's what the name of this thing is. Okay. So if f of x is continuous, which means there's no breaks on the interval from a to b, and a to b and the interval is divided into n equal subintervals. Okay, this is something we've talked about a lot in class. You can divide it into 4 subintervals or 6 subintervals, or you can divide it into n, which means n allows me to change it to anything I want. And then, so if we divide it into n subintervals, then we can find the width of each subinterval right here. So this is let me get a highlighter while I'm just talking here. Highlighter. So there's the width. We've done this in class quite a bit, that b minus a over n. If the subinterval is 4, it'd be b minus a over 4, etc. Okay, so that's just determining the width of each subinterval. So then we go on and we say, and x sub I is equal to, now this is something it's probably hard to see in this form, but basically this is how we plug in. This is the x values that I'm going to plug into the function to find out what the height of the rectangle is. So this first one is the width of the rectangle. This is the x value that I'm going to plug into f of x to find out what the height is. So if I was to, let me draw a picture real quick to help you understand this. So if we have a picture like this and a curve like this, and we're going from here to there, so the first right subinterval, is going to be right there. So if this is a, that's b, then this thing right here is going to be a plus the first plus 1 change in x. Now if we go to the second one, that is going to be a plus 2 changes in x. So that's that idea of we start at a and we just keep adding the width of the rectangle over and over again, and we plug those x values into the overall function. Okay? So again, this says that x sub I is the right end point of each subinterval. So that would be this first one, this second one, this third one, and we'd have an n number of them, right? So if we understand all that, then the integral evaluated from a to b is equal to this limit process here. Okay, so we're going to use this. I'm going to use this definition of a definite integral to evaluate this integral down here. Now, we could evaluate this integral the easy way, just by taking an antiderivative and using the fundamental theorem of calculus and plug in 4 and 0, etc. Okay? In fact, maybe I'll do that first. So if we do it that way, we would go, the antiderivative of 2x squared would be 2/3 x cubed, and the antiderivative of 3 would be 3x, and we'd evaluate that from 0 to 4. So if we plug in a 4 in there, that'd be 64. 4 times 4 times 4 is 64. 64 times 2 is 128, so that'd be 128 over 3. And if we plug a 4 in there, that'd be 12. And if we plug in 0 both places, we get 0. So this would be 128 over 3 plus 12. So so that would be equal to 128 over 3 plus 36 over 3. And what was that? 164. 164 over 3. Okay? So that's the integral, evaluating the integral using the fundamental theorem of calculus. But if we wanted to use the definition, this limit process, what we're going to do is we're going to say, okay, this is going from 0 to 4, so my change in x is going to be equal to 4 minus 0, and we want n subintervals, so that'd be 4 minus 0 over 4, otherwise known as 4 over n. Okay, so that's my change in x. My x sub I is going to, since it starts at 0, it's going to be 0 plus 4 over n times I. So you can see if we go back up here, that 0 is the a, and the 4 over n is the change in x, and the I, of course, is just the I. Okay? So this is going to cause me to start at 0 plus 4 over n, or in other words, start at 4 over n, and then I'm going to step up by 1, so that means I'm going to actually step up by 4 over n. So I'll have 4 over n, 2 4 over n, 3 4 over n, 4 4s over n, etc. Okay? So that means that my f of x sub I times change in x can be represented with, so let's look at the function. The function is 2 times x squared plus 3. So that would be 2 times something squared plus 3, right? Well, what is the something? The something is, in this case, 4i over n, because it was a 0 plus 4 over n. And of course, all that's multiplied by the change in x, which is just 4 over n. So that's my, that's what f of x dx changes, turns into. So again, up here, this is my f of x, right? And that's my change in x, essentially. So now we can write this limit process. So I'm going to take the limit as n approaches infinity of the summation of I running from 1 to n, because I have n subintervals, and if I go from 1 to n, that's going to give me n things. And I'm going to put this whole thing I just wrote right here. So that's going to be 2 times 4i over n squared plus 3, whole thing times 4 over n. Okay, so I'll pause for a second and make sure that makes sense. So that's the setup of the limit process. So we've successfully converted it from an integral to a limit of a Riemann sum. So now we're going to go ahead and try to evaluate this Riemann sum. So first thing I would do, now I'm not going to take a limit yet, so I'm going to go ahead and write the limit down. And I haven't ran the sum yet or gotten rid of it, so I'm going to go ahead and write that. And I'm going to just simplify this here. So 4i over n squared would be 2 times 16i squared over n squared. Of course, plus 3 is just plus 3. And that whole thing is still multiplied by 4 over n. Okay? And remember, with summations, anything that's outside of the, or anything that doesn't have an I can be taken outside of the summation. So I'm going to rewrite this as the limit of n as n approaches infinity of 4 over n on the outside, and then the summation, I running from 1 to n. And I'm going to combine some of this stuff. So I would have on the inside, let's see, 2 times 16 is 32, I squared over n squared. And of course, 3 is still just 3. Now I'm going to break this into 2 summations. So I'm going to go limit as n approaches infinity, and I'm going to take everything that's not an I outside of the summation. So on the outside of this, I'm going to have 4 times 32, which is 128. That looks familiar to me. Over n, come on, Dad, write this nicely. Sorry about that, guys. 128 over n cubed times the summation running from I1 to n. And on the inside, I'm going to have I squared there. And then over here, I'm going to have plus. Of course, the 4 over n applies to this one also. Come on. The 4 over n applies to this one also. There's my summation, I running from 1 to n. And this will just have a 3 there. And this whole thing is still connected to the limit. Okay, so again, all I did is broke this into 2 summations instead of 1. So I'm taking the summation of this and the summation of that separately, and then adding together. But of course, the 4 over n went with both summations because it's on the outside. Here, the 4n got involved into this 32 over n squared, so it became 4 times 32 is 128, and n times n squared is n cubed. Okay? Now we can evaluate well, we're not going to evaluate, we're going to replace the summations with a formula involving n. And there's a sheet that I gave you, and that sheet, let's see, what did I want to, oh. So there's a sheet that I didn't give it to you, but I've showed it to you in class before. There is a sheet that says if I have a summation that I runs from 1 to n of I squared, that's the same thing as n plus 1 times 2n plus 1 over 2. Is that right? I'm trying to remember it from... I better just look it up. Okay, I'm not remembering it correctly. So if I look it up real quick, let's go to dashboard. Actually, let's go to this 2. Yeah, okay. Where was I? I looked it up on a different sheet. So the summation of I squared is n, i's runs from 1 to n, is n times n plus 1, I totally remember it wrong, times 2n plus 1 all over 6. Okay, that's what it is. So now I'm going to go back over here. I haven't taken the limit yet, so I still have the limit as n approaches infinity. And this is going to be 128 over n cubed. And I'm going to replace this whole thing. So let me do the old highlight thing, because you know me, I like to highlight. So I'm going to take this thing, and I'm going to replace it with this. Okay? And now I have to go back to my pin. So I'm going to put in here an n times n plus 1 times 2n plus 1 all over 6. Okay? And then over here I'm going to have a plus 4 over n, and I'm going to replace that summation. There's another formula that says if you just have the summation of a number, it's just equal to the number times n. So this is going to, well, let's go ahead and go full tilt with the highlighter. So this piece right here is going to be replaced with is going to be replaced with 3n. Okay? So now we've gotten rid of the summations, which is a really good thing because it's hard to do a limit with a summation. So now we can go ahead and try to evaluate the limit. Of course, with the limits, just like summations, you can break them into pieces when they're added together. So I'm going to take the limit of this first piece and the second piece separately. So let me write that out. The limit as n approaches infinity of 128 over 6. I'll just bring that 6 over there. 128 over 6n squared times n plus 1 times 2n plus 1, 1, plus the limit as n approaches infinity of 12n over n. Okay, now as n approaches infinity, this just approaches 12, right? Now, how about this one? Well, the way we evaluate limits as n approaches infinity is essentially, if we have a polynomial over a polynomial, we look at the leading coefficient. And in this case, I don't know what the whole polynomial is going to be, but can you see that the leading coefficient of this thing is going to end up being, let's see, 2 times 128 over 6. I'm sorry, 2 times 128 n cubed, right? Whoops. How did that go to squared? That was a mistake. It was cubed up there and I made it squared under. That should have been cubed. Okay. So we're going to end up with a 2 times 128 n cubed on top and a 6 n cubed on the bottom. Okay, there'll be some other stuff in there, but the leading coefficient will look like this. Everyone buy that? So that means as n gets bigger and bigger, these other pieces become insignificant, and we're really left with this whole just this. And of course, it has that same effect that the n cubes essentially cancel out, and I'm left with just the coefficients. And I can reduce this a little bit. 2 and 6 will cancel, leaving 3. So I end up with 128 over 3. And if you remember right, that's the same thing we got up there, because this would be 128 over 3 plus 36 over 3, which if you add those two together, we get 150, 164. 164 over 3, which is the same thing we got the easy way back up here when we did the fundamental theorem of calculus. So that's the limit process. I think it's worthwhile for you to kind of look through this and see if it makes sense. Try to follow the reasoning. I'm going to set up one more. Actually, this video is getting kind of long, so I think I'll stop it. All right.